Hello, welcome to lecture number 27, and today we want to talk about the book is section 5.11, and in this section, let me switch to black ink here. What we're going to talk about is a comparison of h of z, which we've been spending a lot of time on, and h of s, which was the topic of EE 2220. And so in this section we want to draw some parallels and try to get some understanding of what we've been doing. The basic difference between these two, they both represent information about a system, but in a discrete time system, the time variable is n, which is always an integer. And in continuous time, the time variable is t. T is any real value between minus infinity and infinity. N is an integer, and that causes some very interesting effects. First, let's just compare the frequency response in continuous time and discrete time. In discrete time, we have that frequency response is given by sum x of n e to the minus j omega n, and of course the sum ranges over all n values, and I won't write that down. Let's first show, and we've showed this before, let's first go over the idea that this is a periodic function, periodic in frequency, and the way we can show that easily is just say what happens if we replace omega with omega plus 2 pi. And so we'll replace it here as well. And then we'll expand and factor this exponent. Of course, nothing happens to x of n, but we get e to the minus j omega n. That's when we factor out the first part, and e to the minus j 2 pi n. So this term here, as we all know, as long as n is an integer, which it is for discrete time, this thing equals 1. And so what we've just shown is that this and this are the same, so that this and this are the same. In fact, any multiple of 2 pi, any integer multiple of 2 pi, we would find this equality. Basically, this just says that the frequency response is periodic, and it repeats every 2 pi radians. Well, let's look at continuous time. Continuous time case, frequency response, we have a new frequency variable, big omega. Remember, little omega is normalized in radians per sample, and then big omega is unnormalized, it's in radians per second. Well, we get that by integrating the impulse response function, e to the minus j omega t. I'm sorry, getting that a little bit crowded there. So it's just this integral. Let's see if it's periodic. I mean, it looks almost identical, except instead of a sum here, we have a integral. So they do about the same thing. So why isn't this periodic? Well, let's just check. If I replace, just like I did before, omega with omega plus 2 pi, it seems like we ought to get this periodic result. Let's just plug it in. e to the minus j times omega plus 2 pi, just like we did before. And now we'll factor it. There, so we factored it. Now let's look at this term here. This term here, above, this was equal to 1 because we had e to the j 2 pi n is an integer. So as you know, and we've proven this in class many times, this is just identically equal to 1. However, in this case, when t is not an integer, this is not 1. So this thing in the circle is not equal to 1. It has a magnitude of 1, as you know. E to the j x has a magnitude of 1, but it's not equal to 1. Okay, it's a vector that points at any random location around a unit circle, but only when that vector is at 0 angle is that the 1 vector. All right, so what we've shown is that these are not equal. Okay, not equal. So therefore, this is not periodic. Okay, so they're quite different animals, and all because we've discretized. We've run this through an analog to digital converter, and we sample, and now we're in a time variable that's integer, and so we get very interesting, and it's something we have to deal with whenever we deal with sample data systems. Let me just give a quick example of what this means when we write the frequency response as a plot. For discrete time, we'll write the magnitude response as a function of omega. We might see something that looks like this. Okay, and it keeps going. Dot, 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 keeps going forever, where every interval of 2 pi, and this one's at 4 pi, this is at 0, and it keeps going the other direction as well. Every 2 pi interval on the frequency axis, we get this repetition. All right, let's look at continuous time. Oops, need to get a pen. Continuous time, this might have been the system that we sampled to get this result over here. So we've got h, but now it's j omega, and it might look something like this. Okay, never repeats, never repeats. So that's the frequency axis. This is non-periodic. So to briefly compare this result, we know that e to the j omega is cos omega plus j sine omega is periodic every 2 pi, right? So any function of e to the j omega has to also be periodic in 2 pi, right? So some function like h, a linear function of e to the j omega, also must be periodic 2 pi, which is what we just showed. And this is why we use this notation, because what we have when we find h of e to the j omega is we've summed up a bunch of e to the j omega functions weighted by h of n and raised to a power n, but basically we have a bunch of e to the j omegas, so it has to be periodic. On the other hand, if you think about the continuous time frequency response, it's not periodic. We showed that. So it would make no sense we can't use this terminology anymore. We can't use h of e to the j with now the different frequency variable, because this would have to be periodic, right? Since e to the j omega is periodic, just using Euler's identity, it has to be periodic. but h is not, because h is the integral, and when we take the integral against and multiply this by t, it's different than multiplying this by n. When we multiply it by t and take the integral, we get something that's not periodic. Since this is periodic and the frequency response h of j omega is not periodic, we can't use this anymore. Okay, got it? This would be periodic, but we know that when we run it through the integral, it turns out to be not periodic, so we can't use that notation. So therefore we use this notation for the frequency response.